Hello everyone, we are SciArt students from WYSII School. We are proud to present our project Co-pyrolysis of waste cooking oil and waste polypropylene for bio-oil production. We have divided our presentation into 5 parts. Start with the introduction. The improper disposal of waste cooking oil and polypropylene plastic waste presents significant environmental challenges, while the conversion of these waste into renewable energy sources could provide an immediate solution to the disposal problem. Waste cooking oil or WCO can be converted to biodiesel via transesterification, but challenges like complex steps and glycerol byproduct require alternative methods. Co-pyrolysis, which processes multiple feedstocks together, can enhance yields and quality. This project is to investigate the co-pyrolysis behavior of waste cooking oil and waste polypropylene plastic through field production and engine testing, and to establish both the optimal production parameters and the practical feasibility of waste polypropylene and waste cooking oil co-pyrolysis field as an alternative diesel fuel.
This is the pyrolysis batch reactor design, showing all components and steps of pyrolysis process. In this work, the thermogravimetric analysis showed the thermal decomposition at 315 to 470 degrees Celsius of waste polypropylene, waste cooking oil, and this temperature range was used for co-pyrolysis experiment. And this slide presents the equipment for field properties testing on American Society for Testing and Material Standards. This slide shows the setup test of engine performance and emissions.
Here is the result part of pyrolysis process. Production yield of waste polypropylene and waste cooking oil were different as shown on slide. This variation reflects the molecular structure differences between the two feedstocks. When the two feedstocks were combined in co-pyrolysis experiment, there were notable synergistic effects across mixing ratio. The 75 waste polypropylene, 25 waste cooking oil mixture enhanced liquid yield, achieving 70% liquid yield. This improvement comes from waste cooking oil's role as a hydrogen donor and thermal moderator during the reaction. However, increasing waste cooking oil content to 75% reduced liquid yield, indicating that too much waste cooking oil promotes unwanted secondary reaction. This result suggests an optimal balance between polypropylene and waste cooking oil with the 50-50 ratio offering the best synergistic effects.
The physical and chemical properties of pyrolysis fuels were shown in the table. The kinematic viscosity with range showing a systematic increase. C10 index range 57.58 to 57.92. Flash point range from 35 degrees Celsius to 43 degrees Celsius.
This is the results of engine performance using fuel blend. All fuels show a decrease in brake-specific fuel consumption with increasing engine load. Among the blends, waste polypropylene 75, waste cooking oil 25 show the best brake-specific fuel consumption characteristics. The waste polypropylene 75, waste cooking oil 25 blend show excellent efficiency.
This is the result of emissions. Let's start with nitrogen oxide emissions. Waste polypropylene waste cooking oil blends symmetrically reduce nitrogen oxide with increasing waste cooking oil content. Now, for hydrocarbon emissions in Figure 2, increasing waste cooking oil in blends reduce hydrocarbons. The first figure shows carbon monoxide emissions. Waste polypropylene waste cooking oil blends improve with higher waste cooking oil content, with waste polypropylene 25, waste cooking oil 75 closer to diesel. Next, smoke opacity. Waste polypropylene waste cooking oil blend show intermediate values 58.03 to 60.7%, balancing different emissions mechanisms.
Finally, the conclusion part. The co-pyrolysis of waste polypropylene and waste cooking oil demonstrated optimal synergistic effects at 50 waste polypropylene, 50 waste cooking oil ratio, achieving 70% liquid yield compared to individual waste polypropylene and waste cooking oil pyrolysis. The blend ratio systematically influenced build properties. Engine performance tests reveal waste polypropylene and waste polypropylene 75, waste cooking oil 25 blend exhibited superior characteristics. Emission analysis show that increasing waste cooking oil content generally improve nitrogen oxide, hydrocarbon, and carbon monoxide emissions, though with slightly higher smoke emissions. This result indicates that the co-pyrolysis of waste polypropylene and waste cooking oil at optimal blend ratios present a valuable approach for producing alternative diesel fuel while addressing waste management challenges. This is our acknowledgement. These are all the references. Thank you for your attention.